There are 6 circular trigonometric functions. You should recall them from your basic trigonometry class. They're circular because they're based on the unit circle. Shown at right, the unit circle's equation is x squared plus y squared equals 1. So it's a circle centered at the origin with a radius of 1. We could parameterize any point on the circle. Remember, we had like a terminal side of an angle that intersected with the unit circle at a point xy. The angle was called theta. He began on the positive x-axis. Theta was the parameter to get this point xy on the unit circle. We would simply take the cosine of theta for the x value and the sine of theta to get the y value. So that's called the parameterization of the unit circle, where x is the cosine of theta and y is the sine of theta, and theta is called the parameter which is the angle from the positive x-axis. As theta grows, we got different values for cosine and for sine, and we can trace out this unit circle. Now this parameterization and the unit circle equation together gives the Pythagorean identity. If x is cosine and y is sine, substitution gives that cosine squared theta plus sine squared theta equals 1. That was the Pythagorean identity. It just comes from substituting the parameterization for x and y into the equation of the unit circle. Also, from the circular trigonometric functions, we could create other trig functions. So we here have like a linear graph of them. What happens as x goes from 0 to infinity or 0 to negative infinity, we can trace out the graphs of sine and cosine, and we can define other trigonometric functions. Remember, we could also define cosecant. Cosecant as 1 over sine, and secant as 1 over cosine. We could also define tangent. Tangent was sine over cosine, or y over x. Cotangent was the reciprocal of this, cosine over sine, or x over y. So these had graphs. We could make the linear graphs. We also, most importantly, could take the derivative of these functions or the integral of these functions with respect to x or with respect to theta, I suppose I should say here, since all my trig functions have theta. And that is just a basic review of circular trigonometric functions. There's a whole nother family of functions called the hyperbolic trigonometric functions. They're based on this thing called the unit hyperbola. So here's a picture of the unit hyperbola. The unit hyperbola has an equation x squared minus y squared equals 1, much like the circle, but a minus instead of a plus makes these branches go away from each other instead of towards, so they don't connect. We can parameterize any point on the hyperbola as a function of the parameter emanating from the origin and terminating at any point on the parabola. As x equals the hyperbolic cosine of theta and y equals the hyperbolic sine of theta. We call these cosh and sinh respectively because that's what they look like when we read them. But in this case, theta is not the angle but the area from the positive x-axis to the terminal side with a boundary on the unit hyperbola. So that's a little bit different, but theta is still the parameter. As the area that's shaded there, so as theta changes, we have a different value for the area between the positive x-axis, the terminal side, and the curve. Now if we put these two things together like we did with the unit circle, so we have the equation for the unit hyperbola here and the parameterizations here, we have this identity, the hyperbolic cosine squared of theta minus the hyperbolic sine squared of theta equals 1. It's like the Pythagorean identity, but it's for the unit hyperbola and has a minus instead of a plus. So in this case it matters that the cosine is before the sine, of course, because of the negative, or because of the subtraction. And if we can combine that with Euler's identity, which you may or may not have may or may not remember from trigonometry, e to the I theta is the cosine of theta plus I sine theta. Now put these together, do some algebra, I'll save you all that step. We get the following definitions for the hyperbolic sine, cosine, tangent, and the reciprocals. The graph of hyperbolic sine is here. We can define hyperbolic sine, remember sinh, as a function of x, as e to the x minus e to the minus x over 2. Hyperbolic cosine as a function of x, cosh x, is similar with the plus e to the x plus e to the minus x over 2. And hyperbolic tangent, tanh of x, is still sine over cosine. So if you were to take these identities that I just gave you, kind of out of the blue, but there was derivation there if you wanted to find it with Euler's identity and the unit hyperbola, and sine over cosine gives us e to the x minus e to the minus x over e to the x plus e to the minus x, just like sine over cosine. So those identities hold. And from here, we can reach the other three reciprocal trigonometric functions. The hyperbolic cosecant of x is what happens when we flip over sine, 2 over e to the x minus e to the minus x. Hyperbolic secant, sech of x, is 2 over e to the x plus e to the minus x. And hyperbolic cotangent, coch of x, is e to the x plus e to the minus x over e to the x minus e to the minus x. So all we did was flip over those fractions to make the reciprocal identities. Now, because this is calculus, we're not going to leave it at that. We also have to be able to differentiate and integrate these functions. So the derivatives of them, if you would like to do them by hand, you can. From these equations, you could use this guy and take the derivative and use the quotient rule and the chain rule with the derivative of e, and you could cook up all these derivatives, but we'll save you that exercise for your own time if you're bored. Otherwise, here's what they simplified to. The derivative of sinh is cosh of u with times the derivative of u with respect to x. The derivative of cosh is sinh of u times the derivative of u with respect to x by the chain rule. And the derivative of tanh is none other than sech squared of u times the derivative of u with respect to x. So these look very similar to what you know from your regular trigonometric derivatives, except you'll notice that the derivative of cosh, instead of being negative, is positive. So in hyperbolic trig functions, the derivative of the cosine function is positive. So let's see if we can't infer what the rest will be. The derivative of coch, in regular trig, the derivative of cotangent is cosecant squared. So this is cosecant, hyperbolic cosecant, CSCH squared of u times the derivative of u with respect to x. And in regular trigonometry, circular trig, this is negative, and it maintains that. Here in hyperbolic, the derivative of sech is negative sech u tanh u times du dx, so it just looks very similar to the derivative of secant, which is secant tangent, but we have an extra negative. So these two guys are the weird ones. They're different in sign than the circular trig functions, and the derivative of hyperbolic cosecant is negative hyperbolic cosecant of u times the hyperbolic cotangent of u times the derivative of u with respect to x. So you probably already have these memorized from trig functions. On the circle, just remember the new signs that occur with the derivative of hyperbolic functions involving cosine. Okay, so using these identities, we can rewrite expressions and we can also differentiate them. To take the derivative with respect to x of the function the sinh of 2 natural logs of x, we will need the chain rule. So before we jump into differentiating and integrating these functions, let's use their definitions simply to rewrite and simplify the expression, just to get familiar with using those semi-bulky forms of it. You'll recall that the sinh of x is e to the x minus e to the minus x over 2. So we're going to use that, but with a new argument of 2 natural logs of x, and simplify. So this is the same thing as e to the 2 natural log of x minus e to the negative 2 natural logs of x divided by 2. To simplify this, we'll need some properties of logarithms.